First of all, thank you for still being here Friday evening already. Okay, so thank you very much, and thank you for to the organizers for inviting me. Which when I got the email, I didn't understood very well. Okay, hope they know what they were doing, inviting me to this talk. Okay, first things first. I'm an engineer. Okay, so what I'm going to talk about is applied quantum sensing, but basically what I'm going to talk about is about the path from scientific understanding to applications. Okay, the responsibles for the scientific development, to understand nature and to evolve, are physicists, as you know. Okay, but when it comes to applications and so things, we are talking about engineers. Well, eventually after the engineers come all the economy people. Okay, and we have this interface here that is the technological development. Okay, well, that scientific understanding and all these experiments and those proof of concepts and all the things we have been discussing here, okay, have to be eventually developed, into an actual useful technology that can be transferred to society. And is in that region with physicists and engineer typically collide, but ideally will be they collaborate, okay, to basically, that development. And basically that's what's happened in the first quantum revolution, with the laser development and the, transistors that eventually were taken over by engineers in collaboration with physicists to come the applications. Okay, so now we are in the middle of this quantum 2.0, second quantum revolution, blah, 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 the hype now, every, 2 years or 3 years, we have a Nobel Prize associated to quantum technologies. But the situation, well, a lot of funding, but the situation in sensors and metrology is completely different. Okay, quantum computing may be the future, quantum communications may be the future, but quantum sensing and metrology is the past. We already, for 30 years, we have had, devices, you can buy them, the SQUIDs, superconducting quantum interference devices, are already for purchase for 30 years, Nobel Prize 2025, timely, okay? And they have been used for many things, and we have quantum gravitometers, okay? And quantum metrology is so mature that already 6 years ago, the international system of units was already changed, based on the atomic theory and the quantum theory. May the 20th of 2019, the international system of units was changed, okay? And now we don't have units anymore. By the way, nobody cared about that because, nobody cares about metrology. And actually, this very same year is the 150th anniversary of the signature of the Meter Convention. Did you know that? That was the most important event in history when it comes to trade and commerce. Because from that day on, all the countries in the world have the same units, and they can change, and they can sell things to each other using the same magnitudes. And that changed commerce and human interactions forever. 150 years, nobody cares. Okay, but they will care because now this is the standard, the international system of units we have. And as you see, there are no meters, no seconds, no anymore. Now the international system of units is based on these quantities that are exact, okay? And whoever is able to do an experiment with accuracy enough to realize the different units from this has the standard. And this is going to have an impact in industry, extremely important. So, if quantum sensing is the past because of the squids and the metrology. Why there is so much buzz about quantum sensing lately? Because one thing has changed. In the last years, different quantum platforms that can operate at room temperature have been developed. And that changed the story a lot. Because right now, as Ruben mentioned before, we have room temperature qubits we can manipulate and we can play with. And actually, what is the weakness of the qubits when it comes to communications and when it comes to computing is the actual strength of sensing, the influence of the external magnitudes into the actual behavior of the qubit. Okay, so this is where we are. Now we have devices in solid states like the MV Center discussed by Ruben and Itze, already flew. We have optomechanical cavities already working at room temperature, okay, Rickley atoms, and of course, photonic sensors, because you have an interferometer, you just put one photon inside and you have a quantum sensor, just a single photon. And you can do lots of things. Okay, so these two things, the different platforms that can appear at room temperature, and this very important thing, because this is going to impact industry sooner or later, and actually real industry is working on this, is what actually is driven, the quantum sensing. But let's be clear. The fact that a technology exists, the fact that a technology has been demonstrated, does not imply that it's going to be adopted. You have, history of different things that have been, put into place that they have been adopted. One of these three conditions must be observed. The first condition for a technology to be adopted is that it provides with significant improvements over the features, in this case over classical solutions. In the past, that was happening with the transistors within vacuum tubes. I mean, transistors are much worse than vacuum tubes in terms of performance. They are exponential instead of linear. And the dynamic range is ridiculous compared to vacuum tubes. But there was a significant improvement in terms of consumption and integration capabilities. Okay? So that's one condition a technology might be adopted, because there are significant improvements. The second condition is that it provides with capabilities that are not accessible. It's not just an improvement, but we are providing with capability. This happened with the laser versus thermal sources. Okay, the fact that we have a coherent source from 1960 changed everything. And actually, we were not prepared for that. For many years, remember, the laser was a solution in search of a problem. That was a say. And actually, during the first years, all the research on lasers was making lasers of different things, water lasers, and basically using every single molecule that was at hand to make it lasing. Okay, the joke finished beginning of the 70s, with the semiconductor laser, where people say, okay, this is useful for something. Okay, but we spent 10 years, well, I was not born, believe it or not, I was not born there yet, but there were 10 years, people having fun, doing lasers of different things and just, having fun. Or a third thing, it provides with completely new applications of capabilities. That disruption, for example, was the smartphone. That nobody was prepared for that, okay, for having the computing power in your pocket, compared to a standard computer. So we have to be careful with the hype, okay? Beyond certain niche markets, for example, squid is a niche market, okay? High resolution magnetic field measurements, because remember, measuring DC and low frequency fields, DC and low frequency magnetic fields is extremely difficult, and that's why the squids came to play, just to be able to detect those, for example, for magnetoencephalography. So beyond those niche markets, still to be demonstrated how competitive quantum sensors will be. And we have to be careful with the hype again, and we cannot sell quantum sensing or quantum computer as a hammer, that converts a nail everything it says. So this is my big disclaimer here. That being said, what is my assignment? Why am I here? Because I have to, or basically help, because I'm not doing it myself, I'm useless. I'm basically overseeing the creation of a laboratory with the aim to evolve different quantum sensing platforms and to use them in specific application scenarios driven by end user necessities. So basically the idea is to take already demonstrated quantum platforms from Chempacha, okay, identify those niches, those end users, necessities, and evolve, from those principles to the actual. And you may think that is easy. Let me tell you, it's not that easy. Okay, basically the research line that I already put into place, which is funny because we already don't have a laboratory. Actually, the construction has not started yet. It starts November the 1st, okay? So, but we don't have a lab, but we already have some research lines into place based basically on MV center magnetometry for different industrial applications. I will talk that in the last 5 minutes. And use read-bear atoms. Okay, MV centers. Believe it or not, there have been many proof of concepts of MV centers applied to measure different things. As long as, I don't know how long ago, it was used, I think this was almost, I can't remember, it should be somewhere, but 6-7 years, it used MV center to measure individual action potentials from a unineuronal animal. Paleomagnetism has been demonstrated also. They use MV centers to measure the to basically the magnetic activity associated to the heart, and also for gyroscopes and to detect reactive oxygen species. This is something that also Ren mentioned somehow. Basically the activity of this. So hey, basically we have demonstrated lots of things here. So yeah, we can have extremely high accuracy instrument based on FNSBs. So we are done. Let's sell them. My ass. What we have seen are proof of concepts. Okay, in engineering terminology, TRL3, TRL4 maximum. You have to reach TRL9. And for physicists, I mean, it's something blurry what is there. Okay, they don't really understand that terminology. Okay, so that's why I'm here. Okay, so what is the difference between this proof of concepts and this rat, this very nice rat? Okay, so you have this rat in the lab and you have this high accuracy translation stage, PCT control, and the microscope, and so on and so forth. Okay, so this is a proof of concept, but we want to go from here to here. This is Luis Ojeda performing surgery over a pig. It's not a human, okay? It's a pig using one of my instruments here to assess the proper anastomosis, in reconstructive surgery, in experimental reconstructive surgery procedure. And you may think it's the same. Nope. Okay, there is tons of evolution from that proof of concept to that thing that has been approved to be put into an operation room. We have to demonstrate that we are able to sterilize the whole thing. Actually, the head is here. Okay, so here, this is our head. This is the actual optical fiber coming from here. There is another cable, but there are other things here. Okay, and this must be sterilized, and we have to demonstrate that it can be sterilized, and lots of things. Okay, so we have to come from sensors to instruments that can be taken anywhere. Okay, and basically this is the aim of the lab, and this is TRL 6. Okay, it's still 3 to go, but that's for somebody else. That's for the companies, that's for the people that have to come with a proper business plan and to see, you know, the economic viability of the thing, and it can die there. It can die in TRL 6, no problem. Okay, but the lab, the objective of EHU Quantum Center Applied Quantum Sensing Lab ends here at TRL 6. Okay, because to go to an actual instruments, we need to improve the characteristics, to optimize the component, but most importantly, we need a complete ecosystem, you know, for an actual technology to be implemented. We need people that fabricate the diamonds, the heterogeneous integration, specific building blocks. Ruben was also talking about FPGAs and electronics and things like that, characterization, testing, lots of things. So there is lots of fun there. Most of the people with, most of the things will die, you know, in the road. Okay. I mean, the lucky you don't work on in the biomedical field. In the biomedical field, default is failure. Only 1 out of the thousands molecules investigated end up in a actual, you know, medicine. Okay, and 1 over 10,000 medical procedures end up in clinical practice. Okay. So luckily, physicists and engineers, you know, the default is not always failure, but that's not the bad thing. Okay, but that's the default. So in the last 5 minutes, current developments, of course, they are not being done here in my lab in Madrid, but slowly coming here. So I have borrowed a table from Joseba Zubia that I'm using sometimes. I'm also using the lab here. So we have been developing compact ODMR heads. The difference of antennas, this is something that Ruben, that basically in very compact fashion to actually integrate in equipment. So you don't see here any free space optics. Everything is fiberized. So everything is based on optical fiber. ODMRs, studies of sensitivity. So basically, we have now a sensitivity that is 11 nanotesla per square root of hertz. And you say, okay, that's not a state of the art. Okay, the state of the art is almost 3 orders of magnitude below that. The answer is, who cares? Do you know my application? I have not said it yet. Okay. Be careful, because when talking about sensors and these kind of things, people love to dance what is said the limbo rock. This is how low can you go? Okay. So no, I have demonstrated, you know, 9 picotesla per square root of hertz. No, I have demonstrated 8.5 picotesla per square root of hertz. That is sick. Because, you know, ask me, you know, about your applications. Where are your actual, you know, sensitivity? You need, those are the Rabi oscillations measured on the ensemble, basically match with our theoretical predictions. And now we are somehow ready, when we have the lab, to actually make the proof of concept in the application we want. We were contacted by my usual collaborations in biomedical applications and saying, we have this plenty, there are many papers that say, you know, magnetic fields affect migration and proliferation on cells, but we also know by experience that the human body can handle high magnetic fields without problems, MRI. Can you somehow help us doing that? I say, okay, let's do this. Okay, this is the paper they were claiming, they have this modulating cellular response. So we built for them a quantum microscope, basically, just homemade quantum microscope. And basically, it's just the first calibration here. So we have hydrocarbon microparticles, ferromagnetic particles. And this is the optical picture, and this is the magnetic, picture, and they really match, okay? So basically, the idea of this quantum microscope is to introduce magnetic, gradients, in the skin-on-chip model, and see whether, checking, because we can measure what is the actual gradient to really see whether there is influence. I mean, I hope no. I really hope that the magnetic fields do not do that much things to our, because we may go into difficulties eventually. Okay, microwave-free magnetometry. One of the problems these sensors have is they are very, very complicated because they use antennas and optics, blah, 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 blah. Radio frequency is always expensive, power consumption, swap things, and so on and so forth. So let's get rid of the antenna. And also the antenna is metallic, and in many scenarios, having metals is not wise. And this is something that already been discussed about this steady state level anti-crossing and the ground state level anti-crossing. And what actually happens at those levels, there is actually a change in the actual photoluminescence signal. So if you go to this region and you just do the derivative with the locking amplifier, you basically find regions where there is a linear relationship between the magnetic field and the actual luminescence. Okay, so you can use that slope to actually obtain the magnetic field. But this is something we don't like because intensity there. If you realize in intensity measurements, you are doomed. But we do know that actually what happens in intensity happens to the lifetime. Okay, so we did this very quick experiment. Okay, so I have lasers, blah, 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 blah. Okay, we just have this head here. This is a diamond just at the end of an optical fiber. Okay, so that's a very small head with the diamond. The optical fiber, we will do the optical fiber for the excitation and also the light collection. We take it to the electromagnet, and actually we measure the photoluminescence and the phase curves. Okay, so we don't see the slack and feature because it's an ensemble. Okay, it's not just a linear. But basically, we learned a lot of things, and one of the things we learned is that instead of using this information, we can use actually the change in the fluorescence lifetime around the G slack and the E slack to extract information about the magnetic fields in those regions, and also in the zero, around the zero. And now we have Eric Torrontegui in Madrid doing all the simulations and everything for us to actually model this experimental data, and eventually we will go back again. Again, this is why are you doing this? Because there is a specific user, okay, that has a specific problem that wants to solve, and classical sensors cannot solve it, okay? And he really needs a sensor that is non-metallic, okay? And we have to put something non-metallic inside. So this is the end of my talk here. Okay, I have some bigraphs of discussion and so on and so forth. But I want to give you just two take-home messages, okay? First of all, quantum sensing is a reality. I mean, it's been there for some time. The only thing that has changed is the apparition of these room temperature platforms and the extremely important traction that quantum metrology is actually, pushing in this term. I mean, in clocks and so on. I mean, that you cannot overlook that traction from the quantum metrology. That's the first message. Okay, that this is what have changed. Okay, the second message is careful with the hype. Okay, we cannot evolve everything. We have to really, now there are infinity paths that can be taken from TRL3 to TRL6. There are infinity paths, okay? So we need to focus a little bit, and that focus comes from the identification of actually scenarios that make sense. And the third message is this is fun, okay? Although the default is failure, okay? Engineers and physicists and biologists and, you know, and talking to doctors and talking to, is fun, okay? Then you end up doing nothing, but it's fun. And with that, I thank you for your attention.
Thanks, Pablo, for that dose of reality. And we do have time for questions, which I'm sure. Although I have a very minor quibble before that, which is actually squids, in the sense you were talking, were actually first revolution devices. And the Nobel Prize is actually in the second revolution. So squids were invented in the 1960s,
yeah, but,
both the DC and the RF.
Yeah, but the way the squids work now,
the new squids, yes.
The squids you buy are actually coherence,
Yeah.
coherence interference. Okay.
Yeah, but magnetometry in the old squids was actually all first revolution, not second revolution.
But the squids right now are Clark's child.
That's true.
Okay.
So I'm sure there are questions. Yeah.
So thanks for this nice overview of what the lab will do. You didn't say much about the part of quantum metrology that deals with entanglement, and so with having many sensors in strongly squeezed, strongly entangled states. So do you not see demand for that, or?
Yeah, that's a very good question. The problem is I didn't have time for that. When you said this change in the international system of units was actually to have an international system of units prepared for that. Okay, in the old international system of units, there was no room for that. I mean, the meter was the meter, well, for the speed of light, the kilogram, and so on and so forth. When you do this change and you say, okay, there are no units anymore, we have these constants, and there is actually no privilege realization. Okay, even the kilograms, we have the two ways to I mean, the Kibble balance and the Avogadro's project. That there is even not the preferred. And actually, that also opens the way to actually introduce entanglement and to be the standard quantum limit and go to the Heisenberg's limit associated to those realizations. But for that, I mean, we really needed to change the international system of units and the definition, okay? So that's why I'm saying this has such a huge impact and everybody has overlooked, okay? Because now you have a huge realm to play with that. And actually, there was the only way to incorporate that in metrology, in actual metrology, okay? So that is a very, 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 very good observation, definitely.
Okay, one last question. If not, let's thank Pablo again.